Good morning, everyone. We'll start class in 1 to 2 minutes time. Good morning, everyone. And today's lectures are going to focus on the second Digital Filters 2 lecture, as well as some FIR filter design examples in particular. The Digital Filters 2 lecture that we're doing first is going to discuss how do we go about creating different types of FIR filters for different applications, as well as we'll see some worked examples as to how we go about doing this. And then the FIR filter examples lecture afterwards gives us an idea on the types of questions that will come on your final exam regarding the design of FIR filters in particular. All right, so let's get started with the first lecture here. So typically when you're dealing with filters, the primary concern always tends to be the magnitude response of the filter, because like I said, regarding where we filter out the unwanted signal and then we get the wanted part of the signal, we need to make sure that the magnitude of the signal is preserved or maintained in some form or fashion for that part of the signal that we actually do want. However, in some cases, the phase response also is important. And in audio applications, a good example of this is that the phase response may introduce delays in your signal, as well as it may also introduce echoes in your signal where the delayed signal and then the original signal will overlap, so you might hear one before the other and you get this unwanted echo effect and so forth. And in particular, when you're dealing with distortionless transmission, you're going to have to pay attention to the phase response from your filter design to make sure that you get rid of these unwanted echoes or any delays in the audio signal. A good practical world example of this is like if you ever streaming a live video and you're seeing the people talking but the audio doesn't match up to what they're talking and you're hearing the audio a few seconds later. This is the example of when the phase response doesn't work as expected. So they need to do something we refer to as phase matching to make sure that the audio and video sync back up by adjusting the phase response itself of that filter to begin with. So just to recall, remember, once we start doing filter designs here, it means that for any generic filter in the frequency domain being h omega here, there's going to be a magnitude associated with it being modulus of h omega, and a phase being the angle sign here of h omega as well. So any signal that goes through a system, and the system here could just basically be a filter design, distortional transmissions occurs only if the signal form remains unaffected, and meaning that the output signal may be a delayed and scaled replica of the input signal, as well as such that the phase itself doesn't go entirely out of sync of the original signal itself. But then again, you can just do phase matching to get back the signal back into the original phase itself. So also, the system itself must also amplify or attenuate each frequency component uniformly. So that means the same multiplication factor or same division factor for all frequency components must hold constant throughout the entire filter process. And the delay for each frequency component must be by the same delay factor as well. So if one frequency component is delayed by 5 samples, all the other frequency components in that signal must also be delayed by 5 samples. So once you have distorted transmission in comparison to distortionless transmission, a distorted transmission when each one of these signals here are amplified or attenuated very differently for each one of its frequency components entirely, and the delay as well is also going to be quite different for each one of the frequency components as well. So once it's not uniform, it's referred to as distorted transmission. But if the delays and the signal attenuations are uniform in nature, it's basically a form of distortion-less transmission, because again, you can just amplitude scale and and phase shift back the signal to match to what the signal should be to begin with. So your phase delay of any digital filter that you're going to be designing is just going to be what we refer to as the relative delay of any frequency component in this from the input signal. And this equation is given here, being negative phase of h capital omega divided by omega, where the left hand side here being O omega is going to be measured in samples. And in order to satisfy that distortionless response phase condition, your phase delay must be frequency independent, meaning that it's uniform for each frequency, and as of such, the equation there will resolve to alpha being a constant. So as of such, all frequency components is going to be delayed by a factor of alpha samples. And once you do have this constant phase delay for all frequency components, the design of the filter is referred to as a linear phase filter. And we're going to see why it's a linear phase filter in a little bit when we actually do plot the phase response. So let's examine this following Z transform equation here, which is going to be the prototype for designing our phase filter itself. This sequence here is referred to as a symmetric sequence because if we see here, around the C component, which is Z to the 0, we have Z to the 1 and Z to the 2 on the right hand side, and Z to the negative 1 and Z to the negative 2 on the left hand side. The Z to the negative 1 and Z to the positive 1 has the same magnitude component being B, as well as the Z squared and the Z to the negative 2 have the same magnitude component referred to as A. So this is what we know this is referred to as a symmetric sequence. H of capital omega here would be such that when we substitute Z equals to EJ capital omega into the entire equation. Because we know E of J omega here is also the complex exponential form for cos theta plus J sine theta, where theta could be J omega, all the imaginary parts for the sine instances of this complex exponential will cancel out with each other, because when it's E minus theta, that's going to be minus J sine theta, and when it's E positive theta, it's going to be plus J sine theta. So that negative and positive there will just cancel. The cosines just add together because they are independent of sign change regarding the complex exponential. So When we do this for any symmetric sequence, all the sine components will filter out, will be eliminated, and the cosine components will be doubled accordingly. And this has a constant phase relationship here, because each instance of the phases, when we actually do watch it, is just going to be a multiplication of the other, and this is what we refer to where we had the frequency replication. This is also phase replication as well. So any symmetric sequence that you're going to be dealing with will always exhibit constant phase behavior. Similarly, when we observe the same symmetric sequence that we see here, this is also an anti-causal symmetric sequence because we have positive powers of z. In order to make it causal, we just need to delay the entire signal by z to the minus 2. That way we only have negative powers of z and a constant value. And this z to the negative 2 here is just basically a time delay that we introduce from the z domain aspect. So this means that we just delay the entire signal by 2 samples, which is going to be z to the minus 2 here accordingly. Now the question is, in adding this time delay, how did we affect the phase behavior of h of z entirely? So now that the equation here is z to the minus 2 h of z, and if we put this back into terms of omega, using the complex exponential form for z, this time delay that we just introduced there, because we have e to the minus 2 j omega, and this minus 2 here is an integer, it just basically creates a constant phase delay accordingly, and it doesn't affect the overall linear phase behavior of the entire filter design. So it's still a linear phase process, even though we move from an anti-causal symmetric sequence to a causal symmetric sequence. And any symmetric sequence that we deal with, like I said before in the last 2 slides, will have a linear phase. And any filter designs based on these symmetric sequences will also have linear phases as well. So for example, this filter here, once we start substituting actual values for A and B, it's symmetrical about the constant value of z to the 0, and we have the same magnitude terms for z and the same magnitude terms there for z to the 2 and z to the negative 2. When we actually do plot this, the magnitude response here is given by the blue line, but the phase response here is given by the red line, and we can see here that the phase response exhibits linear behavior. If we assume that the passband here is around the 0.7 to 0.8 normalized frequency band, this entire section here, if we rectangle it, is just going to be where we exhibit only strict linear phase behavior within the passband of the filter. So the digital filter types will depend on the transfer function, and as you saw for FIR filters, it's a feed-forward system, it is not a feedback system. And we saw this in Monday's lecture in particular. For any FIR design, everything just goes straight towards the output. There's no feedback introduced whatsoever. So the question is how do we design a filter to match the order required for the FIR filter design? So typically we start with the ideal filter response, and then we find a finite sequence that best represents the impulse response of this ideal filter. In doing so, we need to make sure that it's a symmetric sequence. We can also start with any analog filter prototype design as well. But in doing so, remember, because it's an analog filter, this is, instead of having a finite impulse response, this is going to have an infinite impulse response. So typically, as t approaches infinity for these infinite impulse responses, the response of the filters approaches 0. And once we start dealing with these analog filter designs, we tend to move more towards designing what we refer to as an infinite impulse response, or IIR filter design in particular. So Your typical digital filter response when you with infinite impulse response designs based on the analog filter prototypes will look like this, where we have some initial response and then it just approaches zero as we keep on going. The alternative approach is that, knowing that the filter is going to approach zero and just remains zero after a certain amount of time, we just stop the response at n samples, so we just truncate it, because all these additional samples here is just going to be wasted space entirely. And truncating the IIR, the infinite impulse response, or the IIR response of that filter, that now means that we've created a finite impulse response, and therefore we can go about creating our FIR filter designs from that infinite impulse response that was obtained from the analog filter prototype. However, in doing the truncation here, by taking only n samples, we will have a variation in the frequency response between the original IIR filter design and the truncated FIR filter design that we're catering for here in this particular case. And this brings an important point here, in that because we did that truncation there, a digital filter design is basically an approximation of the analog filter design. So in the finite series of impulses, if we watch this mathematical equation here, what we can see here is that there's no feedback and there's only feed-forward parts, and the transfer function is just going to be of the form here. When we change it from h of n to h of z, it just truncates here. So where we had delta of n minus m, this goes to z to the minus m entirely. And if we actually analyze this transfer function here, we only have zeros, we have no poles. So this entire thing here, we're just going to be absolutely stable. So what we just now saw there is what we refer to as the truncation design of an IIR filter to create an FIR filter. And that means that we can do this in time sampling, meaning that we can do a window to truncate the design of the samples itself, or we can do frequency sampling. The time sampling, what we just now saw is that we start with some ideal filter frequency response, and a good example of this would be the Lowpass filter, where we had our sync equations. And we knew from like lectures way past in the last previous weeks, once we have this filter design here for an ideal low-pass filter, this rectangular window basically transfers such that if h of f is the window design in frequency, when we go back to h of n, we just basically get a sync function as required. In this particular case, because we are observing that our upper and lower frequencies here are positive FC and negative FC, when we move back from this ideal low-pass filter response in frequency into h of n, meaning in discretized time, the h of n equation resolves to 2fc divided by fs. So fc will be the cutoff frequency, fs will be the sampling frequency, multiplied by the sync function of 2 pi n fc divided by fs. In dealing with the ideal low-pass filter response, remember that time response there is going to be infinite in nature. So that means we know that when we apply our symmetric sequence to our h of n, we need to make sure that we truncate h of n symmetrically in order to do this for the FIR filter design. So we need to make sure that for n, we need to go such that we start from negative n to positive n accordingly, to make sure that the length of the n vector is going to be odd. So a good example of this is that, let's say if we wanted the n vector here to go up to positive 2, we need to make sure for it to be symmetric, it needs to go from negative 2 to positive 2. Similarly, if we wanted to go up to positive 3, it needs to go from negative 3 to positive 3 to maintain that symmetric sequence value. And we'll see this in a little bit when we start doing an example to understand why and how we go about making sure that's a symmetric sequence. That truncation that we did is basically the equivalent of multiplying the h of n sequence by a rectangular window w of n, where the width of that window is just going to be length capital N. Visually, what this means is that if we take the ideal low-pass filter response and then we just drop our rectangular window on top of it, that multiplication that we did there mathematically is actually applied here visually, where we have the n samples here being symmetric in nature above the center frequency. So in doing the multiplication, we just extract out only this part of the signal here with width of n samples. Now also remember, because we did this truncation, that means we impose a period of n samples on the entire signal. And the sample frequency response is going to be different because of this imposing of the n samples on the signal itself. Depending on the number of samples being capital N, this actually will result in spectral leakage, which we saw a few lectures back. So it will introduce the aliasing effect at some point, depending on the width of the window that you use for the truncation of the ideal low-pass filter response. To reduce the effect of the spectral leakage, we just basically need to use a sampling window technique that we saw in our spectral analysis lectures. And depending on the shape of the sampling window, this is actually going to it'll help us taper the transitions being at the ends of that window there to 0. So these unwanted frequency components, it will help taper these down to the 0 part entirely. So a typical example here is that we'll use the Hammond window to assist us with this window design technique to mitigate that spectral leakage that we just now saw. A question that I'm going to leave you guys here to actually do a little bit of research on is that the window function here that we observe, it's a different form from what we observed in lecture 9. And I want you guys to actually do a little bit of research as to why it is a different form from lecture 9 here, when we apply it to our FIR filter designs in particular. So let's start watching an example FIR filter design here. So we're going to consider an ideal low-pass filter with a cutoff frequency of 5 kHz and a sample frequency of 20 kHz. And we're going to see how we go about designing our FIR filter using these characteristics here. So we say FC here is equal to 5K and FS is equal to 20K. And then we start with our ideal low-pass filter equation for H of N, which is 2FC divided by Fs, sinc of 2 pi n Fc on Fs. We can rearrange this such that we get rid of the sinc and we put it in terms of sine. And we can get the shorthand version here of H of N being sine of 2 pi n Fc divided by Fs divided by pi of n. This version here in the yellow block is what you should be using. And reason for this being is that this actually is the universal form that you can use without encountering any errors during your calculations. So this yellow block, that's what you want to use for when you're doing your FIR filter design. I'm putting a note there so that you guys know for sure to use it. If you do end up using the others, depending on how the sync function is programmed or how this calculation here actually operates, you may end up getting the wrong values entirely for H of N. So do use only this form here in the yellow shaded block. This actually will give you the correct values of H of N all the time when you're going about doing this. So we need to make sure that our ideal low-pass filter response here in terms of discretized time H of N needs to be a symmetric sequence. So for our case, we're going to say that we're going to go in between -4 and +4 for N here. When we substitute in FC and FMS here into our sync equation, we see that it resolves to 0.5 sync of 0.5 pi of N. Now in MATLAB, when you actually use the sync function, it says sinc of t here is equal to sine pi t divided by pi of t. And this is why you don't want to use that sinc function in MATLAB, because when you actually compare it to your manual evaluation here using this correct h of n formula, when applied with the sinc function here in MATLAB, you're going to get two completely different answers. So just to reiterate and to emphasize a little bit more, use this form here in the yellow block. You will get the correct answers regardless. If you use the sinc function in MATLAB, because of how the sinc function here is programmed, it's going to give you an entirely wrong answer. So use this yellow form here when you're doing your calculations. So basically, we can just say, because in MATLAB here it's going to be sinc t of sine pi of t divided by pi of t here equivalently. The shorthand version of writing this is h of n equal to 0.5 sinc of 0.5 n, where n goes from -4 to +4. But like I said, don't use the sinc function in MATLAB. Use this yellow form here in particular. Once you use this yellow form here and you evaluate your h of n, you want to get a nice vector values here where the indices go from -4 to +4 for n. We also have our windowing function here to mitigate our aliasing effect that we just saw in the previous slides. So we also need to calculate for w of n here, going from -4 to +4 for n vector. Now that we have h of n here and w of n, we just need to multiply these two across using the dot multiplication for each one of these values here. So we start with -4, go and multiply across there, then -3, multiply across there, -2, and so forth. So in the multiplication of these two, we just multiply each one of those values straight across each other and the vectors. And the result here is what we're going to be using for designing our FIR filter. So remember, we multiply these accordingly to the values of the indices. So this -4 here will multiply by this -4 index, this -3 index will multiply by this -3 index, and so forth as we keep on going. So we get the entire vector of values here for h of n by w of n. We see here that about the 0 index, we have a symmetric sequence, because for 1 and -1 it's the same value, 2 and -2 is the same value, and so forth as we keep on going. So if we neglect the n terms here, which are basically 0, we can write our equation here in terms of z with respect to our indexes. So this -0.0228, which is at -3, would be -0.0228 z to the -3. Similarly, that same negative value, which is at +3 index, is going to be z to the power 3, and so forth as we keep on going. Z to the 2 here is just basically 0, so we can ignore those. Z to the 1 here is 0.2754, so that's how we get these here. And the constant value here was 0.5. This filter design here is a causal filter transfer function because we have positive powers of z. And the highest positive power z here is z to the 3. So in order to get into the anti-causal form, we need to make sure that it's going to be, we delay the entire thing by 3 samples. So we just multiply the entire equation by z to the -3. As such, when we do this, we make sure that all the powers of z in the equation are going to be negative, with one constant value here being z to the 0. Alright. So are there any particular questions about how we go about doing the FIR filter design from this example? Yes, I probably meant we went from anti-causal to causal instead. So yeah, that's what I probably meant. So let me write that in on the slide. So I'll fix that slide accordingly for the examples here. Thank you for that. Alright, doesn't seem like we have any particular questions for the designs, but once we go into the FIR filter design examples, it'll become a lot clearer as to how we go about doing these filter designs and these applications here in particular. So we can see here with the example of using the Hammond window is that if we had the rectangular window that we just use immediately, we have this is represented by our red line here, and the Hammond window is represented by the response by the blue line, and we note that there's a different response entirely when compared to the rectangular window, which was basically the ideal low-pass filter response where we truncated by n samples, in comparison when we actually did the Hammond window here to mitigate our unwanted frequencies as a result of spectral leakage. If we match this to the ideal filter cutoff response, being our ideal cutoff frequency, which was 5 kilohertz, we see here that they still cut off at the required frequency where both of these rectangular windows and the Hammond windows here intersect. So you do match the frequency response required for the cutoff frequency that we did design for. And observing the magnitude and the phase responses here, the magnitude response here is given by this blue line, and the phase response here is given by this green line. Now, note here that the phase relationship here is still linear in nature, whereas the magnitude response here is affected because of how we went about doing our filter design in particular. So what we saw there was the time sampling method. The frequency sampling method is where you can choose a suitable frequency response from any established filter design, and it's usually useful for unusual filter designs in particular. So this is going to be something very application specific. And as of such, you sample the frequency response and then you find an inverse discrete Fourier transform, which will give you the two-sided sequence as required. And then you can find the Z transform and you can right shift that to create the causal filter response accordingly. However, for our course, we do not go into detail for the frequency sampling method. We are focusing only on the time sampling method as seen here for the material of this lecture. Alright, so just to do a little brief recap here, we saw as for symmetric sequences and applying any delays for symmetric sequences, we maintain that constant linear phase behavior relationship, which was discussed at the start of the lecture. And this is important for when we go about designing FIR filters, because when we need to move from an anti-causal form to a causal form, by applying these delays accordingly, we see there that we don't affect the phase behavior of the filter design itself, as well as the phase behavior of the signal that is being filtered. We also note that the only thing that's being affected when we do this is going to be the magnitude, but the magnitude, as required for distortionless transmission, is also going to be affected such that there's a uniform attenuation as required. The phase shift that we also observed there was also a uniform phase shift such that all the frequency components in that signal were affected uniformly by one multiplication, one addition or one subtraction of the delay factor accordingly for the phase. Whereas for the magnitude, it was just a constant multiplication factor, a constant division factor, or constant attenuation factor for all frequency components. When we moved on into the FIR filter design, we saw that if we started with an ideal low-pass filter response, this is actually for infinite impulse response filter design in particular. So to move from that being an infinite impulse response to a finite impulse response, when we use the time sampling method, we basically impose a window of n samples here to enforce that instead of going towards t equals infinity, it now goes up to t equals n, where n is the number of samples. And applying this windowing technique here, we impose a period of n samples upon the signal for our low-pass filter design here, and in creation of the FIR filter, we see here that we also, in doing this, we get the spectral leakage or the aliasing effect as a result. And in order to mitigate this aliasing effect, we need to apply a window technique on top of the FIR filter design in order to ensure that we eliminate these unwanted frequency components as a result of spectral leakage. We also saw that in doing our filter design technique that we need to ensure that the sequence needs to be symmetric. We also, in doing this, we start with the ideal low-pass filter response. We made sure to use the h of n equation with respect to sign. If you're using it with respect to sync, please note that depending if you're using Octave or MATLAB, that sync function is programmed kind of weird. So try your best to avoid using that sync function. Use the sign function that we saw in the yellow shaded block, which will give you the correct results for the h of n values all the time. And then we calculated out our vector for our windows, our window function, and we just multiplied the two accordingly to get our filter vector. And then we just transfer that into our z equation, and then we move from the anti-causal form to the causal form accordingly by delaying the samples accordingly. We also saw that the general outline method here for the frequency sampling method is on this slide, but we're not going to be discussing this any further because this isn't covered in the material of the course. All right, so any particular questions regarding the material of this FIR filter design before we move on to the FIR filter examples in the next lecture? All right, it doesn't seem like we have any questions. All right, so let's move on to the FIR filter design examples in particular. That's this. All right, so this lecture in particular is basically showing you guys what sort of example questions you can get regarding FIR designs And these example questions are basically questions that you may encounter in your final exam in particular. So we're just basically going to be going through these and doing the walkthrough for these as to how we go about doing the FIR designs in particular. So you may be given a question such that a particular application requires the design of a 10 Hz FIR filter, and you're going to have to compare it with the performance of a suitable moving average filter and then the 11 order Hamming window filter in satisfying the application. You'll also be given the sampling frequency which is required for you to design the FIR filter. So we need to see what's going to be the cutoff frequency here, which is required for the FIR filter. In this case, it's going to be 10 Hz, and the sampling frequency, which is going to be 100 Hz. And then we need to see which one of these filters here that we need to design for in particular. So in this particular case, we need to do a moving average filter design and an 11 order Hamming window based FIR filter design, and then compare the two in particular. So for the moving average filter, that means we need to know the number of terms here that's going to be average. And we need to know what's going to be the zero crossing in particular. So the zero crossing here, because we're given our cutoff frequency for the FIR filter is going to be 10 Hz. And that means omega is equal to 2 pi on n. And we also know that when we did the moving average filter design, omega here was equal to common omega by t, such that n here was equal to f of s divided by f of c. So f of s was 100 Hz, f of c here was 10 Hz. So we get n here being equal to 10 values, which is required for our moving average filter. So we use a 10 term moving average filter here because n here equal to 10. The difference equation for this is just going to be y of n is equal to 1 divided by 10, x of n all the way plus n going down to x of n minus 9, which is basically going to be 10 values here in the brackets. And the spectrum of this, if we did have to plot the spectrum, is basically at half that of the sampling frequency. We will have a symmetric sequence here, which will show that we'll have all these values here going for each one of the zero crossings and each one of these amplitudes here for the side low frequencies as required. But basically, once we have the difference equation here, that basically ends the design of the moving average filter, because all we need to calculate for here is n, which is going to be the sampling frequency divided by the cutoff frequency. Now we're moving on to designing the 11th order Hamming window for our 10 Hz digital filter design using the sampling frequency of 100 Hz. We need to have the windowing function to begin with before we can actually design this window in particular. So for the Hamming window, we can use the generic window function here, which is 0.54 plus 0.46 cosine of 2 pi n divided by n minus 1. The first step that we do here is that we need to make sure what's going to be the ideal frequency characteristic. So we need to start with the low pass filter design in particular. And the associated time response for this low pass filter design is going to be h of n, which is given by the 2 fc on fs sync function of 2 pi n fc on fs. But like I said, instead of using the sync function here, make sure you use the sine equivalent of h of n that we saw in the previous lecture. Step 2 here is that we need to truncate that n samples here such that it's going to be odd. So the question basically gave us n because it said you need to design an 11th order filter. So n here basically is going to be 11. Even though that we calculated initially for the moving average filter that n here was 10, we can just go up 1 to make sure that it is going to be odd in particular. But the question basically told you what n was here for the Hamming window FIR design, because it's given by the order of the filter itself. So we're going to say here, because of the 11th order filter, so n here is equal to 11, common n here will go from -5 to +5 because this associates itself with 11 values. So we then calculate out for h of n, which is going to be giving us our vector values. We don't need to do for all 11 because remember this sequence here is going to be symmetric. So once we have our first 6 values here from -5 to 0, it's just basically going to be a reflection going down the road. So this value here is going to map here, this value here is going to map here, and so forth as we keep on going. The next step after we have our h of n vector is to calculate the w of n values. And this also has a symmetric relationship as we see here. So we just need to calculate for the first 6 values, and then it's just going to be a reflection from that one point onwards. So for -1 and +1, it's the same value. -2 and +2 is going to be the same value. -3 and +3, and so forth as we keep on going. Once we have our h of n and w of n vectors, we just need to multiply the 2 of these across each one of the indices. We don't need to do all 11 because it's basically going to be the same symmetric sequence as well. So we obtain our hw of n function here. The n terms here is 0, which basically add no value to our function, so we can just truncate those off entirely. Now that we have our hw of n vector here, we need to break this into a z transfer function. Now remember, because the indices here go from -4 to +4 because we truncated the -5 and +5 here, this is going to be an anti-causal sequence. So we make sure that for each one of those values there and that hw of z vector, sorry, that hw of n vector, we make sure that we match it accordingly with the indices. So this will be z to the 4 here, this here will be z to the -4, this will be z to the 3, z to the -3, and so forth when we write out our anti-causal transfer function. The last step here is to move from anti-causal to causal for our filter transfer function. So we watch what's the highest power of z here, which is z to the 4 here, and we multiply the entire equation here by z to the -4 to make this into a causal filter transfer function. At this point, we're basically finished with our filter design question. If we did have to compare the movement average filter design versus the Hamming window filter design, that means you're going to be required to plot the answers. But in most cases, we will not ask you to compare and contrast these. So once you have the final filter equations, that's basically going to be the end of the question. But if you are asked to compare filter designs for some reason or some design for a project, you need to actually do the plots accordingly to see what the magnitude and phase responses are going to be on this. So for the Hamming window, we can see here that magnitude response, it mitigates the side lobe frequencies accordingly, and the phase response is linear in nature as required. And if we put our 10 Hz cutoff frequency, we can see here that for this 10 Hz here on the x-axis, we maintain that linear phase relationship as well as we have our required magnitude response. And comparing between the Hamming window here and the moving average, we see that the Hamming window here for the magnitude response gives us a way better attenuation for the side lobe frequencies in comparison to the moving average filter, where we still have some magnitudes here for the side lobe frequency. We also see that exactly at 10 Hz here, the green line representing our moving average filter, we go straight to a value of 0 for the magnitude. Whereas for our Hamming window here, we still maintain some magnitude accordingly as required. And this is just basically a zoom up of the comparison of the two in particular. But this is where we're using a 4th order moving average filter to see where it actually would be matching up one. Alright, so typically that's the type of question that you will get regarding how to go about doing a FIR filter design if you encounter these questions in your final exam. We basically will be given the cutoff frequency and the sampling frequency, and then it will tell you you need to design for the moving average filter accordingly and to design for the FIR filter design using a windowing function, and they will give you the equation for the window function. What they will not give you, and I'm backtracking here, you will not be given this h of n equation. So I know this year the exam is basically open book and so forth, but typically if the exam was closed book, you're not given this h of n equation. You are required to remember this in going into the final exam. But like I said, because it's an open book exam, you do have access to that h of n equation, so it makes life a little bit easier when you're doing this question. Remember, when you're using this h of n equation, do not use the sinc function as seen here in the slides. You want to use the sine version, which we saw in the previous lecture that I highlighted and said use that version. Right. So that's basically the only type of FIR filter question that you can get regarding this design for your final exam. And for the moving average, we saw all you need to do is just calculate it for n, which is going to be f of c divided by f of s. And for the FIR filter design using the Hamming windows, we just need to start with the ideal low-pass filter response. We calculate out our vector values for h of n. Then we calculate our vector values for w of n. The windowing function typically is given to you. And then we just multiply the two values, get the anti-causal transfer function, and then transfer that into a causal transfer function by just applying the delays accordingly. That basically will be the end of the question at that point. Alright, so are there any particular questions regarding the FIR filter design example that we just loaded here? Alright, doesn't seem like we have any particular questions. Alright, so before I close off today's session, there's one other thing I want to make sure that I show you guys before we go about, because I know it's going to be an issue later on when you actually start doing these applications. So remember I told you guys to use this form here for h of n, which is when we're doing the Hamming window design, so accordingly for the FIR filter design, and you start with the ideal low-pass filter response. So this is 2 pi n fc divided by fs divided by pi of n. Now I want you guys to note one thing in particular here. So I'm going to bring up Octave, and you may encounter this this problem as well when you start using it in MATLAB and so forth. So let's say fc here was equal for our question, not that one, this one. So fc was 5 and fs was 20. Okay, fc is 5, fs is 20, and then we have our n vector here, which is going from -4 to +4. So n here, -4 to +4. Our h equation was sine of 2 pi n fc on fs divided by pi of n. So h is equal to sine of 2 by pi by fc divided by fs divided by pi by n. So we might get a little bit of an error here when we start doing this. So all right, yeah, I forgot to put an n here. So n divided by pi by n. Right. So one thing to note here is that when we do the calculation like this here in particular, you only get one value for h, which is completely wrong. You don't want to do that. You're supposed to get a vector of values for h, as we saw here in the slides, which is this. So I'm not too sure why this actually occurs when we start doing the division, because when we remove that divided by pi by n, we get a vector of values here for h of n. But once we get h here is equal to h divided by pi by n, and I'm supposing it might be dot slash. Nope, it's not dot slash either. So once we have that division, we're basically just going to get one weird value in particular, and it doesn't work as required. So in some cases here, you're going to have to do this calculation here manually as required for each one of those values. Unless someone figures out how to get the division here to work properly, or if I figure out something else, I will post it up entirely. But there's some odd reason why when you start dividing by pi by n here, your vector values here won't calculate out for h of n. So it comes like, because we have h here, no, that's not going to be h, we have to recalculate back for h here, so that's that. And then I can say h that. No, see, it still doesn't work as required. Right, so because we have a vector of values here for h, each one of these need to divide accordingly by the initial values. So we can be like h of 1 here divides by pi by -4. Which is basically just going to be 0. Then h of 2 here by -3. And you see here that we actually do get our correct values as required. Oh wait, yeah, it did calculate it out, but there's a weird approximation value as we keep on going. So just for safety, just make sure that you do the calculations here manually as required. As we can see here, this value here is just it's going to be 0 because that's 0 divided by some weird value, so that's just supposed to be 0. So just watch out for the approximation values when you're doing this in Octave or in MATLAB, because it's going to give you some really weird values as you keep on going. Alright, so just to go back through the steps here. Okay, so I'm going to clear all. I said FC here is equal to 5, FS is equal to 20, and N went from -4 to +4. And H here was equal to sine of 2 by pi by N by FC by FS. So I made sure I got my H vector here, and I could be like, just to make sure I don't overwrite the H vector, H2 is equal to H dot slash, because we want this to be element, I multiplied by N. And we can get our vector values here as accordingly, but just pay attention to that those round off values here as we keep on going. And you see here, one of them is going to be not a number, and as this is going to be 1 4 3 2 1 0 4 3 0. So this one here is going to be 0, where we had 0 divided by 0, I believe. So yeah, that's why it's going to be not a number, but in our vector values, where we actually calculated that, we had 0.5 here. So this is one thing to pay attention to when we actually go about doing our calculations in particular. Because we'll have sine of 0 here, which is going to be 0 divided by pi of 0. So I'm going to have to review this just to make sure accordingly that was correct. Because all the other values here were 0. I don't understand why we got 0.5 there, but I'll check that back accordingly. So let me make a note here. Check back h of n for 0 value. I'll check that back and just make sure what's going on here regarding to that. But all the other values here were correct regardless. So once I check that back and I make sure I know what's going on, I'll get back to you guys and let you know what went on in regards to that. Alright. Like I said, just be a little bit careful when you use an octave here to calculate 12 for your h values as required. Alright. So that's the only thing I need to check back here, because I know the calculation here basically was not a number, because sine of 0 divided by 0 is just basically going to be infinity. So I'm going to try and figure out why did we get a value of 0.5 there in particular, and I'll post it back on the comments of the videos once I do figure it out. Okay. Alright, so next week's lectures are going to be on the IR filter design, or the infinite impulse response filter design. As well as in Wednesday's session next week, we'll be doing problem set 3. So don't forget to vote on which problems in particular gave you the most issues for problem set 3, and we'll be doing those live in particular as of such. After that, from next week, we only have one more lecture on the following week, which is basically going to be the audio fingerprinting lecture. You will see 2 other lectures, which is going to be DSP examples 1 and 2, but we won't be covering that material and it will not be covered in your final exam. The only important lecture that's going to be covered in your final exam is going to be the audio fingerprinting. So within the next 2 weeks, we will finish teaching regarding the course, as well as on the Wednesday session. In the next 2 weeks, we will be doing problem set 4 as well, and that will bring us to the end of the material for the course itself. If there are any requests for doing practice problems or any feedback that's required and so forth, we can schedule live sessions to do these practice problems, or you guys are free to email me as you are practicing to verify if you went about doing the problems themselves correctly and so forth. Around that same time, I will post up like past papers and their solutions and so forth, so for you guys to actually practice and to see how we can go about doing those particular questions and whatnot. Right, last thing to talk about is that your midterm has been fully graded and we did finish the quality checks on them. So you should get your midterm grades sometime today on My Learning. So once you log in on My Learning, only you will be able to see your own grade via the course shell. Yeah, I just answered that. The midterm marks are going to be given back today, because we finished marking everything and doing all quality checks. Right. So, any further questions before we close off today's session? Yeah, sure. Anything, suggestions, comments? Yeah, that's why I need to check back. For the 0 position, I want to make sure why did we get 0.5. So I want to check that back to make sure, and I'm going to add a comment onto the video. Ah, okay, that's probably why. Yeah, so same thing, how the limit of sum of x divided by x as x tends to 0 is 1. So yeah, that's probably why we got 0.5 in particular. Because it may have actually been a limit evaluation, so yeah, that makes sense. But I'll just double check the math behind that just to make sure as to the reason why we got 0.5. So if it's that limit evaluation, I'll add it as a comment on the end of the video, and I'll make sure that it does work out to that value in particular. So thanks for that. I'll just check back that so that way I know to make sure if it's correct or not. Alright, doesn't seem like we have any further questions at this point in time. So, like I said, next week we'll be doing the IR filter designs and problem set 3. So, until then, take care, be safe, and I will see you guys soon. Later.